This video showcases another sag curve example. You are in engineering surveys. A curve connects a descending tangent of 1% grade and a rising tangent of 5%. Their intersection is at 6 plus 050 with an elevation of 374.5 meters. The allowable change of grade is 0.4% in 20-meter stations. The first requirement of the problem is the length of the curve, then the distance of the lowest point from PVT, and also the elevation of the curve at station 6000. Illustrating the curve, there are tangents of negative 1% and positive 5%. The details of the point of intersection are also provided. They are the elevation of 374.5 meters and station at 6 plus 050. One of the requirements is to look for the lowest point of the curve, which we will label as W. The first question is to look for the length of the curve. Without any idea about PVC and PVT, we have to use the allowable rate of change, assuming that N is the number of stations. N is solved as the change of grade upon the rate of change. Mathematically, this is written as G2 less G1 upon R, or positive 5 minus negative 1 upon 0.4. Don't get confused about not using the decimal transformation of the percentages, as they all cancel out anyway. This gives N as 15. With 20-meter stations, the length is then 20 meters times 15 stations, giving the length L as 300 meters. Next is to look for the distance of the lowest point to the point of vertical tangency. When dealing with highest or lowest points of the curve, use the grade diagram. Start with negative 1%, connected to positive 5%. And since we are looking for the distance of the point to PVT, we create a triangle with S2. The ratio is then S2 is to G2. Take a bigger triangle, making the ratio L is to G1 plus G2. Placing the figures from the example, there is S2 over 0.05 as equal to 300 over 0.01 plus 0.05. S2 is then equal to 250 meters. The point of inflection from the grade diagram is the location of point W. The third question looks for the elevation of station 6000. Knowing that with half of the length, which is 150 meters, we reach PVC. Station 6000 turns out as 100 meters away from the point of vertical curve. If the solution is analyzed backwards, from the unknown elevation of station 6000, take the vertical height y to have it approach the tangent, and take the height of this tangent point using the elevation of PVI. Y is derived as 4h with the square of x over L squared. H is solved as an 8 of L with the summation of the gradients. H is then 1/8 of 300 with negative 0.01 minus 0.05, which makes 2.25 meters. Plugging the values into y, we get 4 times of 2.25 with the square of 100 all over 300 squared, giving y as 1 meter. From the tangent point, take the vertical distance to the PVI elevation, and this is taken as the gradient times the gap of these two stations. H is then 0.01 of 50 meters, which is 0.5 meter. With all heights already identified, work on the elevation. So starting from the known elevation of PVI, which is 374.5, add the height of half meter to have the elevation of point Q, which turns out to be 375 meters. Then add y of 1 meter to reach the curve. Thus, the elevation of station 6000 is 376 meters.